This is Group H2O No with Group Leader Mahdi Hassan, Group Members Joseph Ainsworth, Greg Bricker, Nick Grabo, and myself, Kyle Ruff. We did our project on high temperature water gas shift. The objective of this project was to produce hydrogen gas from a high temperature water gas shift. We looked at hydrogen production versus an economical reactor design. Our goal is to produce 500,000 kilograms of hydrogen gas per day while still having creating a reactor that makes economical sense. Some assumptions we made in this project. We assumed that the reactor was isothermal. We did this by cooling down the reactor. The catalyst doesn't age. The catalyst decays much slower than the reaction proceeds, showing that we can ignore the aging of the catalyst. The reaction rate no rate reduction is due to we have no rate reduction due to H2S in our reactor. Since we don't have H2S entering the reactor, we can assume that there is no rate reduction. The effectiveness of this reactor is 1. The catalyst we used is 72% iron oxide and 8% chromium oxide. We used this particular catalyst because there was a lot of research done on it. So we wouldn't have to put our time and our money into researching a catalyst that is effective. We picked a catalyst that had a bunch of research done on it so that we could get right into creating a plant to maximize our profits. A little bit about the reaction. Our reaction ran at 350 degrees C. At this temperature, the K equilibrium is going to be 21.26. The desired reaction for our project is going to be carbon monoxide plus water becoming carbon dioxide and hydrogen gas. The undesirable reaction in our project, the undesirable reaction is going to be the catalyst deactivating, which means the Fe2O3 actually becomes Fe3O4. We looked at some common parameters and how they would affect the reaction. So when it comes to pressure played no significant role, had no significant effect on the reaction. Temperature, on the other hand, greatly affected the reaction. If we increased the temperature by 5 degrees C, the conversion dropped by 20%. If we increased the temperature by 10 degrees C, the conversion dropped to about 45%. The mass balance we used for this is going to be the change in conversion over the change of length is going to be equal to the rate of reaction of carbon monoxide times the cross-sectional area and the bulk catalyst density over the initial molar feed rate of carbon monoxide. The energy balance is that the energy is going to be equal to the overall reaction rate of carbon monoxide times the heat of reaction. These graphs show how the mass balance was used. So over on the left we have a Levenspiel plot, and we use this to find the conversion. We took the conversion and the feed over the reaction, and we integrated under the curve to find what our conversion would be. We then, from that, created a graph that showed conversion versus length of the reactor. Length of the reactor to find how long our reactor would need to be. So for our reaction, we created a PBR reactor with 42-inch pipes, each 20.9 meters long. What we fed into the reactor was 3.62 kilomoles of carbon monoxide per second and 5.43 kilomoles of water per second. We fed water in 50% excess due to water being a lot cheaper than the carbon monoxide, so economically it made sense to add excess water to get a better conversion for the carbon monoxide. Each tube has 193 kilograms of catalyst in it. The reaction was ran at 350 degrees C. We need 110.6 megawatts of cooling to keep our reaction isothermal. The conversion rate of our reactor is 0.83. This is 90% of the equilibrium conversion. It wouldn't make economical sense to get a higher conversion rate since we would need a much larger reactor and a lot more energy put into the reactor to keep it isothermal. We used a PBR reactor instead of a fluidized CSTR reactor because the PBR reactor used 20,000 kilograms less catalyst than the CSTR. There are a couple safety concerns with our project. So the reaction is run at a very high temperature. So we would insulate our reactor to prevent anybody from getting burns. We would also have an auto shut-off if the reactor ever gets too hot. If for whatever reason the heat exchanger wasn't working and the reaction was getting too hot because it is an exothermic reaction and it would continue to heat up, instead of letting the reaction run away, we would have an automatic shutdown that if the temperature got too high, the reactor would shut down. The reactor would shut down. Due to the high temperature, the stresses, you have heat-induced stress on the reactor. So we would have a regular wall thickness inspection to make sure that there are no cracks in our reactor. We would also set up carbon monoxide monitors in our plant so that we could see any carbon monoxide leaks. We have some environmental concerns with our reactor as well. So carbon monoxide, as we said, it can leak. Carbon monoxide can cause a lot of harm to anybody who inhales it. So to avoid anybody getting injured or even possibly dying from carbon monoxide poisoning, we would have carbon monoxide sensors all over our facility. Carbon dioxide and refrigerants are both very bad for the environment. Both of them cause global warming and deplete the ozone layer. And thank you.